Hello everyone, welcome to 𝐿ustraca. So in this lecture, I am going to discuss about the modal participating mass ratios. So many of us have seen this particular term in our code, and also we have seen it in softwares also. We are getting some percentage or in a ratio in terms of modal participating mass ratio. In 𝐸𝑡abs, in STAT, any software, if you go for dynamic response spectra or it's a modal analysis, you will be getting this particular you can say term, and we do check as per the codal provision that the modal participating mass ratio should be, or the percentage of modal participating mass should be 90 to like more than 90% when we are adding up all the mode participations, right? So now, what is this modal participating mass ratios? So obviously, when we are talking about modal participating mass ratios, we have to go for the modal analysis, right? So in this lecture, I am not going to do the modal analysis manually, you can say in depth, because it is a long process, and in some other lecture, maybe in 2 to 3 lectures, I will be breaking it down and I will try to make one series for the modal analysis. Okay, in this lecture, I will be specifically focusing on the modal participating mass ratios, and I will assume that you have a fundamental idea about modal analysis also. So basically, if you see here, we have a you can say structure of 4.5 meters span along the vertical direction. I mean the y direction. Suppose if I just write it the axis like this, suppose this is y and this is x plane direction. Okay, and this is suppose z, which is my vertical direction. So and this is z. I am seeing this cross section. This is z and this is y. Fine. So now if I see the elevation, and you can see that the height of the bottom story is 4 meter, and other two stories are of 3 meter 3 meter, and the total story weight, okay, the story weight of this particular structure, this is I have written from one of the examples. Okay, so it is the total story weight for the top story, it is 2343 kilonewton. For the intermediate story, it is 3538 kilonewton, and for the first, you can say, floor, it is first story, which is 2716 kilonewton. Correct. So what we can do, we can convert this particular problem in a simple multi-degree of freedom system, right? So we can convert it like this. Suppose this is my mass. Let me draw it like that. Okay, stiffness, another mass, stiffness, another mass, and some stiffness. Okay, and this is my support. So what I can write, this is my mass 1 m1, this is mass 2, and this is mass 3. So what we consider when we do the I can say seismic analysis, we consider the structure as a lumped mass system. Correct. So we consider that all the mass for the particular story is I can say concentrated at a particular point at the floor level, where we have the diaphragm, or I can say slab, and that concentrated mass, and this story, at every story, whatever the stiffness that is provided by the vertical elements, we consider it, suppose k1, k2, and k3 for every story. So this m1 value, we know this m1 is you can say 2716 for the story 1. So m1 is 2716 kilonewton, m2 is 3538 kilonewton, 3538 kilonewton, and m3 is 2343 kilonewton. So 2343 kilonewton. Stiffness also we can easily find out based on the size of the column and number of columns. Okay, so and the fixity condition, considering that, we can easily find out the stiffness of for each direction, for x and y direction, right? So this k1, k2, k3 also we can find out easily. Now after finding out this k1, k2, k3 and the masses we have already, we can create the mass matrix. We can create the mass matrix, which will look like something like this. Suppose diagonal matrix M2 M3, it will be 0 0 0 0. Let me write it properly. Actually, it will give you wrong information. It will be something like this: 0, sorry, M1 0 0 0 M2 0 0 0 M3. So diagonal matrix we create always, right? So this is the mass matrix, and if you see the stiffness matrix, so the stiffness, I am not explaining the concept of these things, which if you need, please do let me know in the comment box, so that I can create more such I can say the fundamentals of the stiffness and mass matrix creation. So I will try to make those later on. Okay, so if I create the stiffness matrix, it will be something like this. Suppose K1 plus K2 minus K2 0. Okay, here it will be minus K2, then K2 plus K3 0. It is also, you can see, diagonal matrix, so then it will be 0 minus K3, and last will be plus K3. Okay, so these are the stiffness and mass matrix. If you create, once you create, then you can put the values of mass and stiffness. Okay, and after solving the mode shape equation, the characteristic equation for mode shapes, so if I just write the equation, the characteristic equation for mode shape, so that is k minus omega square n multiplied by m. So this is mass matrix, stiffness matrix, multiplied by in, okay, equal to 0. So if you once solve this equation, you will be finding the lambda 1, lambda 2, lambda 3, and you will be finding out the mode shape coefficients for this particular structural element in each direction. So suppose in one particular direction we are getting the mode shape coefficients in such a way for first three fundamental modes. Suppose the first, sorry, I will write it, mode shape coefficients for first three fundamental modes in one direction, in one plane direction, I will write. Okay, so it will be like this. I would write it like this. Suppose, okay, this is my structure. So after solving it, actually I have the solved example, so I'm just writing it from there. Okay, this is the first three levels, so it will be something like this. Okay, here I have the fixed support, so the value here it will be 1.0, here it is 0.908, and here it is 0.690. okay, this height you remember these heights, it is of 4 meter, it is of 3 meter, it is of 3 meter. Okay, fine. So these are the mode shape coefficients. So this is my mode 1. And what is this? So this is basically, we write it in terms of phi ik. I is nothing but the number of mode shape, and k is the number of floors. Okay, so it will be is equal to phi 1 1, it is equal to phi 1 2 second floor, it is equal to phi 1 3, right? I think I have written correct or what? No, sorry, I have written in the wrong manner. It is actually ith floor k number mode. Sorry, actually it is written in our code also. If you see, phi ik is the mode shape coefficient at floor I in mode k. So it will be just opposite to this. Mode I, floor I. So floor I mode k. So floor I means first floor, first mode, second floor first mode, third floor first mode. Correct? Similarly, if I write the second one, so I'm just writing the mode shift coefficients after solving this equation. Okay, so this is a long process. I will show you later in another video. So it will be something like this, then the next floor, then the next floor. Okay, so here we will get like this, then we will get like this, and then we will get like this. Correct? So here also it will be 1.0. Okay, it will be 0.124. It will be 1.046. Remember these values, when you will be getting, suppose for this particular mode, when you will be getting these values, it will be something like this. It will be something like written mode shape 2 is equal to, so we will have a matrix like minus 1.046, then minus 0.124, and then it will be 1.0. So you'll be getting something like this. This direction, this value, you can say sign that you are getting minus, it will give you the direction, in which direction it is moving actually, and the value is nothing but the mode shape coefficient. Okay, so in this case what will be this? So it will be phi 1, it will be all positive, right? So it will be 0.690, 0.908, and 1.0, something like this. And for the mode 2, you'll be getting this way. So this negative sign is telling that the mode is, or the, you can say the vibration is happening in this direction, or you can say the displacement is happening in this direction. Okay, in the opposite direction. Now similarly for the third fundamental mode, which are the main governing modes actually. So I'm just drawing these three governing modes for one plane direction, remember. So it will be, now this will be here, now this will come this side, correct? So it will be something like this, then it will be coming like this, then it will be coming like this. Okay, so it will be again 1.0, this is 1.343, and this is 1.036. This is my mode 3, and if I just write it in terms of matrix, it will be 1.036 minus 1.343 plus 1.0. Correct? So this much, this is a big calculation which you have to solve, and finally you will be getting the mode shape coefficient for one plane direction, and also the similar way you have to do for the other plane direction also. Now after solving it, what is this modal mass participation? Now let's come to this particular point. So if you see in our code IS 1893 part 1 2016, in page 24, okay, clause 7.5.4, simplified method of dynamic analysis of building. So here you will get this modal mass mk of mode k is given by mk equal to summation of wi phi ik, you know, mode shape coefficient. So summation of wi phi ik square divided by g is nothing but the acceleration due to gravity in the current units, multiplied by summation of wi phi ik square. Okay, so wi I know for each floor level what is the I can say weight of the floor, I know, right? So I would write like this. Suppose let us consider for mode 1. So I'll write for mode 1. Okay, so I would write something like this. Suppose top floor, intermediate floor, and suppose first floor. Okay, so top floor, if I just write Wi, I will write it Wi here. So for top floor, Wi is, what is the value of Wi? I will just write it from here, 2343 kilonewton. So once I write here 2343 kilonewton. For the intermediate floor, it is 3538 kilonewton. And for the first floor or the bottom floor, you can say it is 2716. Remember, this is nothing but the story weight of the story. Okay, so now this is my Wi. Now phi ik for the first mode I know, correct? First phi ik for the first mode I know, so I can simply write it here. Sorry, let me take it in green only. Yeah, phi ik. So for the first mode, for the top story, what is the value? So it is 1.0. For the next story, it is 0.908, 0.908. And for the next story or the first floor, okay, it is 0.690. Okay, now what I need? So I need Wi phi ik whole square. Okay, or you can say Wi phi ik. Okay, so if I just multiply this, I need here Wi phi ik. Okay, so simply you just have to multiply these two. So it will be 2343. Fine, this will be how much? 3538 multiplied by 0.908. So 3212.504, 3212.504, and the other one, which is 2716 multiplied by 0.690. It is 1874.04. So 1874.04. So this is Wi phi ik. Okay, phi ik means in one mode 1 story 3, mode 1 story 2, mode 1 story 1, like this. Okay, ik. So mode shift coefficient. So we did the seismic weight of the story multiplied by the seismic coefficient. Modal coefficient. Fine. Now what we need? Now another factor we need, which is Wi phi ik square. Okay, so Wi phi ik square we need. So for first one it will be same because this is 1, so 2343. The next one it will be 3538 multiplied by 0.908 square. So it is 2916.954. Okay, so 2916.954. And the next one, if you see, it is 2716 multiplied by 0.690 square. So it is 1293.088, right? 1293.088. Now if you just do the summation of Wi phi ik is equal to how much we will be getting? So if I just do it, 2343 plus 3212.504 plus 1874.04. So it is around 7429.544. So I will write it 7429.544. And how much I will be getting here? It will be summation of Wi phi ik square. Okay, so it is equal to 2343 plus 2916.954 plus 1293.088. So it is around 6553.042. So 6553.042. Correct. So now what we need this. You see here we need this mk. So this mk, now in this case this k will be replaced by 1, okay, because this is for mode 1. So I can write m1 equal to how much? So the formula is summation of wi pi ik whole square, correct, divided by g multiplied by summation of wi pi ik square. So this is the formula, correct. So now for this mode 1, if I just put these values, so it will be 7429.544 whole square, okay, divided by g multiplied by 6553.042. now if I just change this, if you see, if I convert this to Newton, okay, if I convert this to Newton and basically this one, okay, so what I will get, so it will be 7429.544 square multiplied by 10 cube, and if I write this g in terms of meter per second square, so 9.81 multiplied by 6553.042. so basically we will be getting this in terms of kg, okay, because I have converted this first in Newton, then I am dividing it by 9.81, okay, multiplying it by 9.81, so it is converting to kg, okay. So how much we will be getting? So if I just write it here, let it write 7429.544 square, okay. What I will do, I will keep the 10 cube separate, so 9.81 multiplied by 6553.042, so we are getting 858.642, we can say, right? 858.642 multiplied by 10 cube, this much kg we are getting m1. So this is the mass, that vibrated during the creation of mode 1, okay, or in the mode 1 this much mass, 858.642 into 10 cube kg mass vibrated, okay. Now what is the total seismic mass that we have? So if you just add this, okay, so if I just summation of wi, if I do, how much, what is this total seismic mass? So total seismic mass you will be getting, let's see, because here I don't have any live load, so I am considering only with dead load. If you have live load also, then 50% or 25% live load need to be added, okay. So here I am taking 100% of dead load, so 2343 plus 3538 plus 2716, so this is my seismic mass, 8597 kilonewton, 8597 kilonewton. So if I just write seismic mass, m equal to, so suppose I will convert it to kg, so it will be 8597 10 cube divided by 9.81, okay, so it will be 876 point, let me do it, actually I forgot how much it was, 85 97 divided by 9.81. Okay, 876.35. Okay, 876.35 multiplied by 10 cube, this much kg. So this is my seismic mass, and this is the modal mass for mode 1. Modal mass means the mass that is vibrated, or you can say in the mode 1. Okay, so now if I want to find out that how much mass, or how much mass from the total seismic mass is vibrated in the modal mass 1, or you can say in the mode 1. So how much percentage of mass of the total seismic mass vibrated in the mode 1? Okay, so I can simply write it that maybe you can write it here. Modal mass contribution to seismic mass by mode 1. Modal mass contribution to seismic mass by mode 1. Okay, so how much it will be? So this was my total seismic mass, so it will be total seismic mass is this one, and on this much mass vibrated, so it will be m1 by m. So if you just do it like this, 858.642 multiplied by 10 cube divided by 876.35 multiplied by 10 cube, how much we are getting? So 10 cube gone, so you can simply write it that 858.642 divided by 876.35, so it is 0.979. so 979, this is the ratio, modal mass participating ratio. So this is what my modal mass participating ratio is for this mode 1. Okay, for mode 1. Now if you convert this to percentage, so it will be it will be 97%, right? 97%. So that means 97.9 something. So 97.9% of this seismic mass vibrated in the mode 1 itself. Okay, so this is what this modal mass participating ratio is. So for that, this whole modal analysis you have to do, then only you can get this particular answer actually. Okay, so this particular things normally we do in the software itself, we do not do manually. But if you want to see for a simple multi-degree freedom system or single degree freedom system, I may make I can say small video on that also. That is possible. But basically this is how this modal mass participating ratio is being calculated or being achieved. Okay, so now suppose I will open the software, and here you will see modal participating mass ratios. If I just go to show table, and I'm taking suppose for one direction, suppose mode 1, here the mass participation is, or modal mass participating ratio is 0.833. That means 83% of the seismic mass vibrated in the mode 1 itself, this for this particular direction. Correct? For this particular direction, this much percentage of mass participate. Now if you see this sum of ux, sum of uy, what is this? Suppose I have calculated the mass participated, I have calculated the mass participation for mode 1. Now similarly I can calculate the mass participation for mode 2, mass participation for mode 3, for one particular direction I am doing. Okay, So if you add all the participating ratios for each direction, you will see that finally you will get the 100% of mass, or here 95% of mass is participated. If you increase the mode number in this case, so it will be increased. Okay, it will be to up to 100% also. So that means that the total seismic mass vibrated in all the modes. Okay, so here what we are getting, as we have taken a very ideal condition, that in the first mode itself 97% of the seismic mass vibrated. So if you find out all the three modes, you can say mass participation for all these three modes, and if you add up, you will see that almost 100% mass has vibrated in this particular situation. Okay, so I hope it is clear how the modal mass participating ratio is being achieved. So obviously, for more clarification, you have to understand the modal analysis, how the modal analysis is being done, how this equation is being used to find out this mode shape coefficients. So that I will make a explanatory video on this if required. So I hope this particular thing is clear, and we have this you can say the method given in our code also. Okay, so you can simply check this, and you can try to cross check your ETABS or software results also. Fine. So this is it for this lecture. If you have any doubt on this, you can always write me in the comment or in the chat. I will try to answer as per my knowledge. And if you have any, you can say suggestion for further contents, please do let me know. I will you can say try to make contents of your choice, or you can say on your suggestion. Thank you, and see you in the next lecture.